Now that we've got our minds wrapped around double integrals over rectangular regions, I'd like to talk about the idea behind a double integral over a general region. So first thing I'd like to do is consider a function of two variables. We'll say z is equal to f of xy, and then we'll let d be a region in the xy plane. Now I believe that the reason that they go with d rather than r is because r typically gets used for rectangles, and d could be considered a domain within the xy plane. So here's just a general, peanut-shaped region within the xy plane, more specifically quadrant 1. So what we would like to consider is the volume that's contained below z equals our function and within the given domain D. Well, that volume is going to be equal to, as we saw in the previous section, the double integral over the region D of f of xy dA. Now, the unfortunate thing that we have associated with this is that we can't necessarily slice up D into a bunch of little subrectangles because we have this boundary around it where we're not necessarily going to get a rectangular shape. Now, because we do know how to find the volume over a rectangular region, one quick fix that we can do for it that really does absolutely nothing to let us know how this takes place is we can define a new function and a new region. We can define this rectangle R, and then we can say on the rectangle R, we are going to let g of xy be defined piecewise. And we will define it thusly. It's going to be equal to f of xy in the event that xy is within the region D. And it's going to be equal to 0 if the ordered pair xy is not in the region D. Now this is a bit of a cop-out, but you have to admit that if you define it this way, then the double integral over the rectangle R of g of xy dA is going to be equal to the double integral over the region D of f of xy dA, which allows you to turn this double integral over a general region into the double integral over a rectangular region. Well, that takes us right back into the last section, and now we can evaluate it. Now, unfortunately, that doesn't give us an adequate way of actually evaluating the double integral. It just lets us know that this is possible. This is a thing that we can do. So rather than going with that, what I'd like to do is define a couple of region types that we can have within the xy plane. There are a total of 3 different types of regions within the xy plane. Now, unlike, binary things, one doesn't have to be one or the other. It can be both. It can be a multitude of different possibilities. So a type 1 region in the xy plane is going to be defined in terms of inequalities. So suppose that y is bounded between two functions of x. We'll call them g1 of x and g2 of x. Then x will be bounded between a and b. So a general idea of what a type 1 region would look like is we would have a top function, we would have a bottom function, and then we would have two x values like so. The region in question would be the region that's contained by these two functions of x and these two vertical lines. Now, this is a type 1 region. For a type 2 region, we're going to go ahead and reverse the roles of x and y. We'll say that x is bounded between two functions of y, we'll call it h1 of y and h2 of y, and then y is bounded between two constants, c and d. So we have a larger function, we have a smaller function, and then we have from c to d. So a type 2 region would look kind of like this. The important thing is that for a type 2 region, x is defined as a function of y, and for a type 1 region, y is defined as a function of x. Now there is a third type of region, but we're going to get into that in the next section, so we're not going to worry about it here. So in the next video, we'll go over some examples of type 1 or type 2 regions and how to set them up as such.